Werner's theory of coordination compound. In today's lecture, we'll talk about what is Werner's theory, how it is used, and how it is significant to us. Currently, coordination compounds constitutes a very significant portion of our lives, whether it comes to your cancer therapy, treating of heavy metal poisonings, and to make colored photographs as well. The entire discussion regarding Werner's theory or the coordination compound was started in 1898, while Werner was doing study regarding colligative properties. And accidentally he come upon the conclusion that he have found something new, which he in that time called as coordination compound. Although this theory was given at a time when even the electrons were not known. So the entire discussion was left just at a basic theory. But later, after about 20 years, Werner was recognized as the father of the coordination chemistry because of the entire discussion that he started. So starting on, the father of the coordination chemistry, the title is given by to Alfred Werner. Alfred Werner, who gave this theory in the year 1898 and was awarded Nobel Prize in the year 1930, actually about 15 years. In the theory, before giving the theory, he was doing an experiment regarding your colligative properties. Colligative properties are what? Those properties which depend on number of particles. So he was looking for your first electrical conductivity and depression in freezing point for the compounds he was working with. Depression in freezing point. So he was working with a salt of cobalt chloride with ammonia as a solvent. So he made different solution with different concentration of cobalt chloride and different amount of solvent. While doing the experiment, he found that all the solution that he have prepared, they all are giving different answers. That means the properties that I am checking for electrical conductivity and depression in freezing point, they were different than he was expecting. According to him, the complex that he was taking, this ammonia in the ammonia solvent, this cobalt chloride salt get converted into different forms with the different chemical formulas, including cobalt hexamine chloride, cobalt tetramine chloride, and cobalt Cl3, and finally cobalt NH3 whole 5 Cl3. So he found that these different compounds in the solvent were behaving entirely differently. In this, he found that the colligative property resulted that there are about a total of 4 ions that are responsible for the conductivity. Here, in this, it was found that there are total of, here should be 1 Cl also, that there are total of 2 ions that are responsible for conductivity. In this, it was found that there is only 1 ion responsible for conductivity, and this, it was found there are total of 3 ions that were responsible for conductivity. So using the corrective results from the colligative property as well as of our electrical conductivity data, he concluded that although the salt was same, the solvent was same, but because of a slight change in concentration, he was getting a different result. So he came upon a theory that he has discovered something new, which he called in that time as coordination compounds. Coordination compounds. The first person who ever started this discussion, and he gave certain postulates which were entirely based on experimental logic. There was no theory behind. Okay, there was no scientific theory backing it. It was just a theoretical explanation which he figured out from the experimental data. And according to him, that in coordination compounds, in coordination compounds, metal exhibit two types of valencies. Two types of valencies, which he termed as, first one being primary valency, second one being secondary valency. From the primary valency, he stated that primary valencies are ionizable. Primary valencies are ionizable and equal to the oxidation state of the metal ion. How we can explain it? So let's suppose if I have this complex, cobalt NH3 OL4 Cl2, having one Cl on the outside. According to him, the primary valencies are what? Which when goes into the solution, because of the solvation effect, they undergo solvation and get dissociated into their respective ions, and they produce the ions based on what are the species which are lying outside this coordination complex. Based on that, he said that whatever the charge is produced here, this charge will always be equal to the oxidation state of the metal if it were forming a normal compound. So for example, in cobalt chloride, it was cobalt present in 3+ state because Cl exhibit -1 oxidation state. The same oxidation state will also be exhibited by cobalt in the complex as well. Then he stated that the secondary valencies that we are talking about, the secondary valencies are non-ionizable. That means no matter what you do, you cannot ionize them. Non-ionizable and equal to coordination number of metal. So what does this mean? This means that if a complex is found by the secondary valencies, they will lie inside here, and in the solution this portion is bound by some force which at that time was unknown to us. He said by these secondary valencies, even if they go into any kind of solvent, they refuse to undergo ionization, or water's solvation effect will never be strong enough for any given solvent. It will never be strong enough to separate this portion from the metal. And these valencies or these forces are collectively called as secondary valencies. Now, based on how many different types of species this metal can bind with, that is called as your coordination number, where the coordination number he referred to as the number of sites a metal can bind, number of site metal binds with the binding ions, which he later called as ligands. These were your ligands. So the secondary valencies are non-ionizable, and in the solvent they do not get separated in the constituent ions. Also, in the postulates he further added that whatever the ions or the metal ions and the ligand that are bound together, they are bound together in such a manner that their binding leads to a characteristic three-dimensional arrangement of species in the complex. So, in the fourth postulate he added that the binding of metal and ligands by secondary valency leads to characteristic three-dimensional arrangement, 3D arrangement of the ligands around metal center. For example, in the case of this cobalt NH3 whole 4, these 4 ammonia ligands were found to be bound in the plane of the metal center, while 2 of these Cl were found to be bound above and below the plane of the ammonia. And the Cl which was outside, because of the entire charge carried by this entire species, a Cl minus ion was there to stabilize the opposite charge on this complex. This three-dimensional arrangement is characteristics of secondary valency, and this geometry particularly called as octahedral geometry. Now, these were the postulates that Werner gave to explain. But, like I said, the theory was given at a time when electrons were not known. So that means whatever concept of bonding of ionic covalent that we are talking currently, they never existed. So this theory ended at this particular point without any explanation of why this particular geometry is being attained, how it is attained, and what is the nature of this secondary valencies that is enabling the molecule to not go under ionization. So, with these answers left behind, apart from these geometry, he also added, he did further experiments and classified that using the coordination number or how many ligands are present around the metal center, you can define the geometry. So that means it is not just limited to cobalt, it can be applied to various metal ions. So he found elements with coordination number 4 can exhibit 2 different geometries. One being tetrahedral, other one being square planar. With elements with coordination number 6 can exhibit octahedral geometry, and elements with coordination number 5 can exhibit trigonal bipyramidal geometry. These geometries can be represented as having your metal center at the very center, and in case of tetrahedral, the molecule will be found to be bound like this in the tetrahedral environment, giving tetrahedral geometry. For square planar, the metal center will remain at the center with all the constituting ligands around it bound in the plane, and this is your square planar geometry. Why? It is square planar because the ligands are bound at equal distance from the metal center. For TBP geometry, if the metal center is at the center and three of the ligands are bound to it in the plane, forming a triangular plane, while two of the ligands bound to it above and below the plane, giving us a trigonal bipyramidal geometry. A pyramid having a triangular base above and below the plane, and that is called as your TBP geometry. What kind of limitations? Limitations for Werner theory. Although Werner theory was very successful, it explained and it opened an entire new branch of chemistry which we call today as the coordination chemistry. But despite of that being so early in the history, it was very difficult to explain various phenomena that are associated with different types of coordination compound regarding their bonding, their nature, their properties such as magnetic properties. Some coordination compounds were found to be attracted by magnet. Some were found to be repelling the magnet. Some had extremely vibrant color. Some other had pale color. These were such properties which cannot be explained by the means present at that time. So the limitations were what? Limitation number one, that it cannot explain nature of bonding. Why? Because electrons were never there. So that means there was no concept of bonding, because every single bonding that we explain is always in terms of electrons only. So it cannot explain nature of coordination bonding, nature of coordinate bonds. Coordinate bonds. Second, it cannot explain color, geometry, and magnetic properties of coordination compound. Magnetic properties of coordination compound. So, this is all about the discussion regarding the coordination chemistry. And now we have figured out how coordination chemistry was derived, what are the actual scientific logical bases that were used, and how Werner came to the conclusion that he have found something entirely new, the coordination compounds, and what are the limitations that this theory suffers. Although, despite of this limitation, because it can explain the structure and how the coordination compounds are actually existed in nature, these are the reasons that led to the discovery coordination compounds are important to us. Okay, that's all for now. If you have any doubts, you can add it to the comment section and we'll get back to you.